Okay, welcome back. The next part of state feedback control, we talked about linearization. As you can see, in order to apply state feedback control, U equal to KH plus KR times R, and K defined based on the matrix A and matrix B. So what if we have a nonlinear system? It means the state equation has this form: h dot equal to any nonlinear function of h of u, and sometimes also has disturbance. So we cannot design state feedback immediately because we don't have the information on matrix A and B, right? So we need to do linearization to have this approximation model. So this one is just approximate of this one, okay? The idea is that when we design controller K and KR for the approximate system, we expect that the controller would work well with the actual system as well. Alright? So now let's see how we can linearize a nonlinear system. So given state equation h dot equal fh and u and y, the output equation equal to a function of h of u. And so the first step, for a system, when we want to control, one type of control is regulation. A regulation means you have a reference R of t as a step. Okay, so this is for regulation, which means you want to regulate your output to be a constant. Okay? So the reference is just step. And this means that we have the equilibrium point for the state. It means we desire state to converge to equilibrium. Let me give you an equilibrium of a pendulum. Let's say we have pendulum like this. Okay. So this is the angle. For this pendulum, if we don't we just bring it to a certain angle theta like this, and we release it to have a free motion. And suppose there is friction here, then the energy stored in the pendulum would dissipate through the friction here, and finally it reach equilibrium here, right? It will stay here when t go to infinity, right? So this is called equilibrium, and to be more specific, it's called stable equilibrium. If you have a pendulum like this, actually if you carefully hold it at the angle that is that is aligned with the direction of gravity, right? You make it aligned with gravity, then it can have equilibrium in here, right? But if you have a small disturbance, just small push, just a little bit, can be, if you act on it a little bit, or maybe just too much wind push on it, right? Just a little bit, Yeah, just push it a little bit. Okay, and then it fall down. It fall down away from the equilibrium here. So this type of equilibrium is called unstable equilibrium. Okay. In order to find equilibrium, so at equilibrium the state is constant. So actually HE is constant because it stay like here, for example, like this equilibrium. I can write equation for you. Actually that equation it looks like this: theta double dot plus a constant times sine theta equal to 0. Is that so? What is equal to 0? Let me see. Yeah, without the input, right? So we talk about okay, let's say a free motion. There's no control input. So if I write it into state space, static representation, let's say that h1 equal theta, h2 equal to theta dot. So h1 dot equal to h2 and h2 dot equal to minus a sine h1, right? Correct? So now you have a function f, so you have h, which is h1 and h2 like this, right? Then you have h dot equal to h dot equal to h2 and minus a sine h1. So this is your function f, right? This is f of h without control input. With control input you would have b times u here. Okay, so you have b times u here. Then you can have plus b times u. So this is a function h and u, right? So now you want to find equilibrium, because h equilibrium means h constant, then h dot equal to 0. So here I choose h dot equal to 0, h equilibrium dot equal to 0. Then we have h2 equilibrium minus sine minus a sine h1 equilibrium plus bu equilibrium equal to 0. Then we can have h2 equilibrium equal to 0 and minus a sine h1 e plus bu e equal to 0. Suppose we want equilibrium to be at angle 0, I mean at h1 equal to 0. Okay, I mean, okay, suppose we don't want to inject any input UE, but we have a stable system. Okay, okay, suppose we don't inject any U, but okay, which means UE equal to 0. So here you have minus a sine h1e equal to 0. Then what you get? H1e equal to 0, both 0 plus k pi, right? So you can see that theta can be 0 or theta can be pi at the equilibrium, right? Yeah. This means that by finding equilibrium using this equation, you can find both stable and unstable equilibrium. You just need to check which one is stable, which one is unstable. Yeah, actually we can check that. If it's a high dimension system, we can just check the eigenvalue of matrix A when we linearize it. But now it's not really linearized system, right? Now it's non-linear system. So once you have equilibrium and you want to know whether only two ideas here. Linearization is useful for two ideas here. First, you want to know that the equilibrium is stable equilibrium or unstable one. Then you linearize around the equilibrium first. Okay? And then you can take the eigenvalue of matrix A of your linearized system. Also, you can design controller based on the linearized system. Now let's look at the process finding equilibrium value, the matrix A, okay, or the linearized system around equilibrium. Alright, so how can we do that? Well, actually we can do it using Taylor-series expansion. So first, from the equation h dot equal to fh plus b f of h of u. Then we want to linearize around h equilibrium, so we define h as h equilibrium plus something, right? Plus delta h. So any h can be rewritten as h equilibrium plus delta h, right? If h is far away from h equilibrium, delta h is large, something like that. So yeah, similarly, u equal to u equilibrium plus delta u. This does not look very nice. So I change it a little bit. Okay. So now you have this equation, and then you make this Taylor-series expansion of this function. Okay. So any function, any nonlinear function can be expanded using Taylor-series by this term and then plus the first term. So this Taylor-series expansion, you try to find the, we call this the expansion around equilibrium, around h equilibrium, right? And delta h is h minus h equilibrium, right? Delta u is u minus u equilibrium. Okay, you can find from here, you can find from here. So finally, here you have h dot equilibrium plus delta h dot, right? Yeah. So h dot equilibrium equal to f of h equilibrium, u equilibrium, right? So this just cancel with this, right? So finally you only have delta h dot equal to This one is called A delta H plus B delta U. And from here you can design controller. And if you want to control it around the equilibrium, which means delta H is 0, then you just find the controller delta U such that the state delta H convert to 0, right? Yeah, so now you just have linearized system, a linear system. Then you can design controller easily using state feedback or using RQO, right? And here is the illustration of the controller architecture. So from non-linear system, you approximate it to be a linear like this using the linearization process. Okay, and so here delta H equal to H minus H equilibrium, delta U equal to U minus U equilibrium, and this become the input of the system, of the control system. And delta Y is the output. Okay, it's the output system of the system. So the structure of the control you design, you can design delta U equal to minus K times delta H, right? But how can you compute delta H? Delta H is just H minus H equilibrium. And how you get H? You compute from the dynamic system. Okay, so dynamic system here, to be precise, actually input U to the IFHU, you have H dot, and then you use one integrator, you get H, right? And so when you have delta H here, and then you add with U equilibrium, then you can have U for your system. And here is the scaling controller or scaling coefficient in order to have Y track reference R. Okay, so here you have so here actually you can define, you can have how can I say, in order to find KR you have to, okay, look, so you want Y to track R of T, and but from the equation here, because for H equilibrium, if you inject U equilibrium, you will get H equilibrium, and from H equilibrium you can compute Y equilibrium, right? So the scaling factor can be designed. Okay, so if you have delta H, which is H minus H equilibrium, times C, then you have approximately have Y minus Y equilibrium. Okay, So instead of so first you cannot have y approach RT directly, but you can have y minus y equilibrium approach to R minus y equilibrium, right? So if you design KR in order to have y minus y equilibrium approach to R minus y equilibrium, you get KR. Okay. So let's say the reference here, just call it, what can I call here? Okay, I can call here as okay, let me multiply R minus y equilibrium by KR, so I can have KR times R and minus KR times y equilibrium. Okay. So, okay, let's say for the output you can measure y, and then okay, let's say u equal to ue plus delta u, and delta u equal to minus k times delta h and plus kr times what? For linearized system you have delta y here, so it times R minus y equilibrium, like this. So we can follow the same process, we can compute KR. So actually here to build the control architecture correctly, you should use something like this. This one is not R, but it is plus minus, so here is y equilibrium, this is R. Okay, and how you get the y equilibrium? If you have H equilibrium, then you can multiply it by you can multiply it by C. No, you can use a function H, right? H of H equilibrium, U equilibrium. Yeah, actually this way is better. And yeah, all right, so do you have any question? And we need U equilibrium as input here as well, so you need to have from here. As input, right? Yes. So So this is the complete control architecture for a nonlinear system using controller designed from linearized system. Okay, now let's practice one example. The example that has nonlinear spring. So the spring this is called a leaf spring. So its property is not linear. So the equation to describe the motion of the leaf spring on the vertical axis, like this, defined by this equation. Okay. H1 is the horizontal position of the axis, and H2 is its horizontal. Let me check. H1 is the horizontal position of the chassis. H2 velocity. I think it's supposed to be okay. So the chassis connects on the spring here, right? Connect on the spring here. Suppose so this part supposed to be fixed with the wheel. So the chassis here can have motion up and down, right? Up and down due to the spring's displacement. So actually this equation is supposed to be for defining position on vertical axis, but here I guess this is a mistake. It's supposed to be vertical. Okay, and mass can be the mass of the chassis, and the spring here actually there are like 4 spring, right? Yeah, for spring. If we have back wheel and front wheel, 2 for back wheel, 2 for front wheel. So all right, so this is the equivalent equation for all the spring. For example, just make it just try to simplify it. So the original equation is like this, and then we transform into state space like this, and then we can have nonlinear term on the second equation, right? So we have F1, H1, H2, F2, E1, H2. For the F1, it's already linear. We don't need to linearize it. But for the F2, it's non-linear. Then we follow the process of non-linearization. But first, find the equilibrium. So equilibrium, F1, H1, H2 equal to 0. Then H2 equal to just 0. And then F2 of H1, H2 equal to 0. Then we can have, I think we have here, right? Yeah. H2 equilibrium 0, and then we have this one and this one, and then we can find H1 equal to 0 and H1 it can be equal to plus minus square root of this. But because K1 and K2 are all positive, then this one does not exist, right? Equilibrium in the time domain. Now we are still talking in the time domain, so no complex number. Okay? So the equilibrium is 0, 0. Then we linearize the system. Like I said, the first equation already linear. We even don't need to care about this. But you still can use the linearized process. Now the most important is the f2. So take the time derivative with respect to h1 first, and then we substitute all of this h by the equilibrium, right? So we substitute 0, h1 square here is 0, then we only have minus k1 over m, right? And then we take the time derivative with respect to h2, and because there's no h2 in the second equation, then it is just 0. So finally the linearized system is just like this, very simple, right? It's like we ignore the third order term. I mean the not third order, you can say the term with the h power 3, right? All right, then we can design controller for this system. Yeah, so here we only talked about dynamic system without control input. There's no U here, right? Because this system we don't control. What we can learn from this is that we can study from this that how the motion of the taxi behave, right? When, for example, when we display the spring to a certain distance, let's say when the wheel drive over a stone, then it's like the spring initially pushed to a certain distance compared to the taxi position. No, I mean the wheel here from here. If this one step of the stone is like this one try to push up a little bit, while this one maintain still the same position, and then we can observe the motion of the taxis. All right, so we don't control it. And so what if we have control input? What should we do? Let's say for equation of pendulum, like here, where is it? Oh, I think I already escaped. Yeah, pendulum here, right? So if we have equation h1 dot equal to h2, and then h2 dot equal to minus a sine h1 plus bu, right? So the equilibrium point for the second equation, the first equation of course I can write it down, h2 equal to 0 like this, and then for the second equation I have a sine h1 equilibrium plus bu equilibrium equal to 0. So in some sense here, it's like, well, we decide equilibrium at some point. Let's say I want the pendulum to be inverted, to be up. So I choose h1 equilibrium to be pi, right? Or this one is minor, right? Then u equilibrium, yeah, choose. Then b equilibrium supposed to be 0, right? So now we can linearize the system. How can we linearize it? Well, how you can linearize? So we take the partial derivative. So this one is f1, right? This one is f2, right? So I talk only the second equation. Partial derivative of f2 with respect to h1 equal to, here we have derivative of sine, you have cosine h1, and then we substitute h1 equal to h1 equilibrium, which is pi, right? So here you can have cosine of pi, what you have, minus 1, yeah, minus 1. So you have a, yeah, you have just a. How about equilibrium? Okay, how you find partial derivative with respect to u, h2 first, sorry, h2 equal to what? There's no h2 in this equation, then it's just 0. And partial derivative f2 with respect to u equal to just b, because this actually already linear. You don't even need to find the partial derivative, right? It's already linear. Alright. Second case, if I choose equilibrium at 0, I mean the pendulum is just straight down, then the difference is only this term, right? All the other terms are still the same. So if I find f2 partial derivative f2 over h1, I have minus a cosine h1, and then I substitute h1 equal to 0, right? So now I have what? Minus a, right? So something interesting here. Yeah, a actually positive number. So if you have a positive number, and let's write down the linearized system of the pendulum. Okay, this system. Let me write down. So I go to white screen. So h1 dot equal to h2, which is 0 h1 plus h2, and now h2 dot equal to, when we linearize here, we got a, right? A h1 plus 0 h2, and then plus u, bu, right? Okay, this is case 1, h1 equilibrium equal to pi. Another case, h1 dot still 0 h1 plus h2, and h2 dot equal to minus ah 1 plus 0 h2 plus bu, right? This case h1 equilibrium equal to 0. Well, let me write in the matrix form. I can write matrix form like this. Matrix A here is 0, 1, A, 0 times H plus 0 B times U, right? This one H dot equal to 0, 1 minus A 0 times X plus 0 B times U. So you look at here, yeah, A is positive. So from this, can you evaluate the which one is stable, which one is unstable. If we don't inject any input U, if we don't control it, we want to know the system stable or not, it's converged or not. How can we check it? We can look at the eigenvalue of matrix A here, right? A in this case, A in this case. Now let's check. Let's check the eigenvalue. Yeah, actually the eigenvalue is minus A and 1 for this one, and this one eigenvalue is A and 1. Why? Because if I just change H1 to be at the bottom, H2 at the top, wait, if I change H2, I change the equation 2 to be the top, right? And then wait, H2, but A is time H1. A is time H1. It's still off diagonal, right? So let's check with MATLAB or SciLab whether eigenvalue of this one is negative or positive. Eigenvalue of this one negative or positive. Let's find out, right? Yeah, let's find out. Right, Ali. So we have the off diagonal, right? Off diagonal. All right. So two cases. The first case, A equal to this and eigenvalue, one is positive and one is negative, then the system is unstable. For the second case, matrix A to be like this, and the eigenvalue is complex conjugate, purely complex number. Then the motion is oscillation. Yeah, it oscillates forever if there's no friction, because in the model we did not introduce friction at the hinge. So energy can be just transferred from kinetic energy to potential energy, back and forth. Okay. So, all right. Okay, maybe I just note here it's a pendulum model. Okay. All right. So I think the linearization for the lecture part is already complete. Then you can just simulate these two the system here, right? Yeah, just try to simulate the system. So there is a little mistake. Need to modify something. For the nonlinear system, we choose initial condition to be like this, and if we choose the equilibrium for H1 equilibrium, or why is this H1 equilibrium equal to 0, H2 equilibrium equal to 0, then we have linearized system around this equilibrium to be like this. And then let's choose initial condition, same initial condition. So this pi over 6 is away from equilibrium. So this one, we don't talk about equilibrium at all because we don't linearize it. So we just take pi over 6 as initial condition, which is away from the vertical axis, so like this. So we take it away from this, so this is initial condition, h1 at time 0 equal to pi over 6, like this, and initial velocity is 0. Okay. So when we simulate this one, we expect it to look similar to this one. But if we linearize around pi, around the unstable equilibrium, so for this case we choose h1 equilibrium equal to pi and h2 equilibrium equal to 0. So in order to compare this one with this, we need to choose the initial condition for this one to be pi, or more or less around pi. So should not be exactly as pi, because if just use exactly pi, then this one equal to 0. The right hand side is 0. This one also 0. Then we just get stable result, or just constant h1 and h2. But for this case, for sure that the system is unstable. So now you simulate the case 2 here and the original nonlinear equation here, and make comparison. Okay. So we want to compare the nonlinear with the linearized system at around pi. We should initialize this one h1 at time 0 equal to pi over 6 and plus a little. Okay, and for this non-linearized system around pi, around the unstable equilibrium, we can initialize it from 0.01. All right, and then we can make comparison. And when you compute delta h here, don't forget you need delta h plus h equilibrium, right, to get h. Then this h can be compared with this system. Okay. So you use one constant for equilibrium 2, and that constant should go into the initial condition, right? Oh, yeah, there is a mistake here. This is supposed to be pi. Okay, so to simulate it in a easy way for observation, for analysis, just use pi minus like this. So it means the pendulum move up. Okay, it means we move the pendulum up almost 180 degree like this. So from here to here it is pi minus 0.01. So the pendulum will fall down back to 0 and then to the negative part for the linearized system. But for the linearized system, it just approximate. During the first 4 seconds, the simulation result more or less this one, same as this. But after that, the simulation of the linearized system drift away from this one because it's going to be unstable. For this one is going to be diverge, but this one is going to oscillate from the effect of the sine h1 here.